Hello everybody. I'm glad you were not frightened by our title of this next talk and decided to join us for Hannibal, the AI Lector. First of all, to the remote viewers, please, during the talk, at any time you can post your questions in the Slack channel for this talk. And for the audience here in the room, please, after the presentation, just raise your hands and we can answer questions from the audience here afterwards. So I would like to introduce our speakers. So first of all, Tilman is a junior professional at TNG, and he developed Hannibal as his internship project. And in the meantime, in his master's thesis, he is discovering planets outside of our solar system. And we have Andreas, who earned his PhD in the field of nano-optics. He has extensive experience building machine learning solutions. And at TNG, he works as a senior consultant and full stack developer. Tilman and Andreas will take us on an adventure through literature, exploiting neural networks, audiobook creation, deep dive into cloud automation, and other challenges encountered during their creation of the Hannibal software. Thank you.
Yeah, hello everybody. Thanks a lot for the nice introduction, Patrick. Today we will present Hannibal, the AI Lector, which is the project that Andreas and I have been working on for the last 1.5 years, basically. Our talk is split into two parts. First, I will present more of the scientific part of the question. Then Andreas will explain a bit more about the infrastructure and cloud architecture aspects of Hannibal. For this project, we worked together with a producer of audiobooks, an Austrian company called BOOKSTREAM. And the problem that they brought to our attention was a problem with audiobook quality control. Basically, in the process of producing audiobooks, they usually receive or produce tens or even hundreds of hours of recorded speech per week. And doing quality control on these massive amounts of audio is quite labor intensive. Basically, it involves people called lectors listening to entire audiobooks and searching for errors in these audiobooks, basically. And then these errors that they might find in the recordings are noted down by them, passed on to the cutters, who then has to do corrections on the audiobook, or maybe sometimes even parts have to be re-recorded. And then after that, this is my schematic representation of what a lector looks like. Nice orange person. And he or she has her eyes to the left at the actual book that was supposed to be read. And then on the right side, he has his ear, which is listening to the actual audiobook and then trying to find errors. And these errors, from now on, I would call them discrepancies, because they're basically a discrepancy between the audio and the book that was supposed to be read. These audiobooks, these discrepancies can be of several different types. I just show some examples here. For example, if the lector hears on the sandbanks, again, it's just a duplication of some text, which is obviously not desired. Then on the sandbanks, the rabbits as little gray, it's just some words are missing, so it's an omission. And on the sandbanks, many of the rabbits, just some additional words were inserted by the speaker, by the reader. So this is also a discrepancy, just of the insertion of some words. This is not an exhaustive list. There might be other errors within audiobooks, but these are some of the most common ones. So for Hannibal, the goals of the project were basically to automate and maybe even increase the reliability of finding these discrepancies, because an AI obviously will never lose focus, and listening to tens of hours of audiobooks, you can easily imagine that you might miss some discrepancies that are in there. And then the system is supposed to present these potential discrepancies that were identified to the lectors for review. And in this way, the lectors should have some more time. It should free up some time of the lectors to actually focus maybe more on the artistic aspects of the audiobook and more on the style of the reading and so on, which is more difficult to do for an AI. The solution that we came up with, in order to explain it, I will introduce a metaphor of crossing the stream. Here we have a nice picture of a river in Alaska, I think. And the left side of the river is supposed to represent the realm of the audio, the recording of the book. Then the right side is where the text lives. So the actual underlying book that was supposed to be read. And you can imagine the waveform of the audio just running across the left bank, and then the actual text that is expected on the right bank of the river. And so the problem becomes that we somehow need to cross this river and compare the audio with the text that we expect. So that is the formulation of the problem, basically. So here we have a more schematic view of the same situation. Again, we have the audio on the left and the text on the right. And now the naive idea, or the first idea that we came up with, was to simply use a speech-to-text engine to convert our recorded audio to a transcript, which we can see here. And then all we would have to do is and we tried this. For the speech-to-text engine, we elected to use a package called Deep Speech, which is published by Mozilla, open source. And there's actually also a German pre-trained model available, which is important because BookSTREAM is an Austrian company and most of their books are recorded in German. And this model is available. So a shout out to the GitHub user Ashishak for publishing this model free to use. But when we tried this, we came across one problem, which turned out to be actually the main challenge in the whole project. And that is the false positive rate in identifying discrepancies. And I'll explain what that means. And the problem was that deep speech itself, when doing speech-to-text conversion, still has a relatively high error rate. So it just cannot recognize all the words that were spoken correctly. And then if we compare the transcript that deep speech gives us with the expected text, with the book, we will find many discrepancies that are not actually errors in the audio, but just errors from deep speech's conversion. And these are then false positives because they are falsely identified as discrepancies. To give you some idea of the numbers, the most recent English model of deep speech has still a word error rate of 7%. And this would give you on average about 10 false positives per minute. And the error rate would be even increased for some audiobooks because they sometimes use old-fashioned language, archaic or very fancy words. Or even if the speaker uses strong voice acting, sometimes he's singing or shouting in the audiobook. So this would even increase the error rate. And then if you have too many false positives, these have to be reviewed one by one by a lector, obviously, to decide whether it's actually an error that needs to be corrected for the final version of the audiobook. And when there's just too many false positives, then it just takes too long to review all of these, and then the whole goal of saving time cannot really be accomplished. And the main, this turned out to be the main difficulty, basically, to find all important discrepancies, all errors in the audiobook, but have still a tolerable false positive rate. So how can we fix this? We need to build this bridge in a better way. Again, the image of the the stream. And in this naive approach, the way we build this bridge is basically starting on the left, trying to build all the way to the right side of the river, which is obviously not how you should build a bridge. Instead, you should start on both sides and try to meet in the middle, which is obviously a nicer way to build a bridge. And it turns out that the way deep speech itself works helps us to build the bridge in this more favorable way. And to understand how, we need to look into a few more details about how deep speech works. Well, deep speech obviously starts by taking in just an audio file, and it converts this to some kind of representation of the audio by taking the spectrum and some other representations, modifications. And then these representations are passed through a recurrent neural network, which does most of the heavy lifting in terms of speech recognition. And then the output of this network is basically a table of character probabilities over time. So in this example, I just show 2 points in time and just 2 characters, and they have some certain probability to occur at this time. And then this matrix or this table still has to be decoded to find the text that is most probable given this probability. This character probability over time. So there's a decoding step, and then we get our final result. In order to build our bridge in the second way, we actually jump in after the probability matrix and don't use this last decoding step anymore. So back to our image. We now only use deep speech half, so only the first part of deep speech basically, to get our character probability over time, which now lives in the middle of the river, let's say. And now we can ask of this probability matrix, how likely is that the text that we expect actually fits in with this probability matrix? So basically, how likely is it that a certain passage was actually read by the speaker? And then if the probability drops between a certain threshold that you have to figure out, then we assume, no, something else was spoken here, so there's a discrepancy, and you throw an error, basically. So this is what we wanted to implement, but how did we do it? The main challenge there was that you can't simply take an entire, let's say, 20-minute audio file, an entire chapter, and then ask, how likely is it that the entire text fits with this chapter? Because this would basically just give a probability of 0, because all these small probabilities for each time step just multiply to give very small probabilities. And furthermore, we want to know where exactly in the chapter the errors occur, not just if the whole chapter was read correctly. And also maybe even what kind of mistake was made. And so the solution to this is not to compare an entire chapter, but to compare the audio with the text piece by piece. And the algorithm that we came up with, you can imagine like a zipper, more or less, where the top, this chain of teeth on the top right corresponds to the stream of character probabilities over time, which we get from deep speech, basically. And then the bottom chain of teeth corresponds to the expected text. And then what this zipper basically does, it checks if the small chunk of text, which is under the zipper at any time, fits well enough with this part of the character probability matrix. So basically, if this chunk of expected text is likely enough, and if this text becomes too unlikely, drops below a certain threshold, then basically the slider gets stuck, gets jammed in there, and we say there must be a discrepancy there. And then after the discrepancy, the slider just has to be advanced a little bit to the right, basically to find a new spot where the text and the audio fits back together, and where we can start the process again to find the next discrepancy after that. Actually, this image is not entirely correct because the two sides, the upper and the lower chain of teeth, are not advancing at the same speed as they obviously would in a regular zipper. But it might be that the speaker reads faster at some point or slower, or there are pauses in there. So actually in the algorithm, the right and the left side have to advance at different speeds to keep the audio and the text aligned. So this is a small detail which is not captured in this image. Before we come to some actual numbers and results, a short word on why the second approach is better. Our explanation is that the decoding step that we showed that deep speech uses in the end to get the most probable text for a given character probability matrix, this discards a lot of information. Basically, it discards all alternative texts that might also fit relatively well with this matrix, but are not the best text. And by taking the expected text directly and going in this table of character probabilities, we use all of this information and therefore can get a more robust result. Okay, now for a short demonstration of what this looks like in use. Just step. Yeah, so this is basically just a small web application to use the prototype that we built. And you can upload a book. You choose the PDF of the book and give it a title. And then it shows up there. And then you can upload an audio file. And in this case, we'll also upload a text file, which is the expected text for this piece of audio. It's not working to zoom in? No. Okay. So basically just give it a title, upload the WAV file and the TXT file, and then hit submit. And now it's uploading the audio file. And now you have the chapter there. It gives you a status in which step of the analysis it is currently at, or if there are any errors, it will show up there. And now for the trick where in the cook show, they pull out the finished turkey from the oven. We ran an analysis earlier, just a very short one. And this is now the list of the discrepancies that were found. And you're shown just a small chunk of the text with the head where the error was found, and then a 5-second chunk of the audio. And then you can review if you think it's an actual error or if it's false positive, or if you're unsure, and also type in a comment. And you can listen to the audio. Can we listen to it here as well, or are they just going to hear it in the webinar?
Yeah, you should hear it on the microphone. So, dann musst du nur mit Zoom. Audio doppelt. Browser. Sorry.
Kaffeetanten 3 Näpfchen mehr als am ersten Sonntagnachmittag. Die eine sagte, sie.
Okay, so this example is in German. but you can listen to it again.
Kaffeetanten 3 Näpfchen mehr als am ersten Sonntagnachmittage. Die eine sagte, sie.
Okay, did anybody catch it? So, yeah, it's typing it. The Oster was just missing in this sentence. So just one part of this long word is missing. Yeah, that's the discrepancy that was found. Great. Thanks. Okay, and now for some more concrete results. Just in general, we found that Hannibal finds about 1 to 3 discrepancies per minute, depending on the audiobook and the speaker. And this gives you then about 0.5 to 2 false positive discrepancies per minute. And compared to the naive approach earlier, this is a reduction of about 4 to 10 times in the rate of false positives. And the required human time to review these discrepancies is about 5 to 10 seconds per discrepancy, just going through this list, listening to the audio and checking the button. And this gives you about 10 to 20 minutes of human time required to review 1 hour of audio. And with BOOKSTREAM together, we did a more in-depth case study as well. And they used an audio file which was 26 minutes long and had 18 known discrepancies. And these were errors that actually occurred in their production, so they weren't artificially put in. And the human lectors found 9 out of these 18 errors, and Hannibal actually found 17 out of 18. And as mentioned, the Hannibal workflow takes about 1/3 of the time of what a human lector would take to listen to the audiobook. And lastly, from my part, there are still some challenges that remain on the part of the algorithm. There are some discrepancies that are basically below the sensitivity of Hannibal at this point. Basically, if a single syllable or character is misread, for example, changing deceive to receive, this falls below the sensitivity, so is mostly not identified at this point. And also if the speaker coughs or there are background noises or parts with low audio quality for some reason, since the system was not really built for that, it doesn't identify those problems either. And secondly, there are some issues just from the deep speech architecture that basically always throw a false positive. For example, when there are numbers in the text. And this is because there's just an inherent ambiguity about how numbers should be read. For example, 1930 could be read like that or could be read like 1930. So the system can't tell which one it should be, and so it always throws the false positives in this case. Also, if there are English words in a German text, for example, Sherlock Holmes drank einen Coffee to go, then this is obviously difficult to recognize correctly for a German trained model. And if the actor also uses very strong voice acting, singing in the text or something like that, this also usually causes some false positives. All right, so far from my part, and I'll give over to Andreas.
So also welcome from my side. We now heard basically how the theory evolves. Nevertheless, theory is nothing if you can't have at a later stage a website where we really do it. So here we are focusing on the techniques behind. And I called it a journey from past to now, or an evolving MVP. The main reason is if we deal with such an, let's say, unusual topic, we should check a little bit our requirements, what we have to deal with. First of all, the first assumption was that we had to deal with 20 to 60 minutes of audio in CT quality, which is roughly 10 megabytes per minute. So we would need file sizes of around 0.5 gigabyte, and of course, similar amounts of memory on the machine for storing this file, and also for the probability matrix, as you have heard of. Also, since the file size is not too large, we thought of a simple upload page. And as a first draft, we thought that we just load up the text file and the WAV file, because that's what the AI basically compares. As we did this, just a short comment on the structure itself is we built a front end. It's a normal React TypeScript front end. Backend was Node, and the AI itself was a Python container. Here it's entirely built into Docker. The main reason here for is that we had to modify TensorFlow to get the probability matrix out of it. So we need custom modifications and had to build it ourselves. And the first deployment itself was just an Amazon Web Service EC2 instance or a machine in the cloud. Also, the basic workflow was rather simple. We upload the text file, we process it, we read the results on the result page as you have seen it. So we had our front end, our backend for front end, which does the uploading and downloading stuff, the analyzer itself, and the hard disk for storing the audio files, and the database for some metadata and storing discrepancies. As we progressed, the requirements changed a bit. First of all, we found out that the most books were available as PDFs, and extracting the text of the PDF so that on a per chapter basis is rather challenging, even for a human. So that we basically lost all our effort in reducing the time, because it's now basically shifted to extracting text from PDFs, which is a quite tedious task. Also, we detected that the upload time was not, depends very strongly on the internet provider. And so for larger files, it sometimes fails. So we came up with the second iteration of the system. And the second iteration now gives us an additional stage, which does an PDF to text extraction. Then you must not upload an URL. You can just upload the wave. You can just give the URL to a wave on your file hoster of your choice. So we fetch it. So we are not now depending on your machine, because if you're uploading it and you're lost to internet connection or close your laptop, then the upload is gone. And we also switched to Google Cloud. Main reason is that we are now not having one machine, but a whole Kubernetes cluster, which can contain of multiple machines, multiple nodes, so that we can scale up the AI to have more processing power. Also, we added a kind of security with a standard key cloak and gatekeeper setup. And for storing, now at the cluster, the hard drive on the node is not sufficient enough, so we use the network attached storage for it. So how does the process look like after the second iteration? First of all, we create the book and upload the PDF. Then you also create the chapter and you upload basically the upload URL. What we're then doing is we had an instant download of the WAV file. We make a PDF to extraction, text extraction. We match the text to the audio, because now we have only the wave or the audio for a chapter, but we uploaded basically the whole book. So we should know which parts of the text we use for the analyzing stage. Then comes basically Hannibal. And after that, we can retrieve the results. We thought we are happy, we met the customer requirements, but obviously not. So, but have a short look at the second iteration, how it's now look like. We have our gatekeeper a security stage, we had the front end, the back end. And now, since we are in the cluster, we can have multiple analyzers running in parallel to speed up the analysis, because we can do analysis for multiple chapters now in parallel. So, but as mentioned, the cluster itself was rather unhappy, or at least we was, the cluster doesn't care about, because first of all, our assumption was wrong that the files are usually lower than half a gigabyte of memory, because we found out that audio files of up to 6 gigabyte are required. And if you imagine that you now need basically the 6 gigabyte to upload or download, and you have to also store them in memory and also store the matrices for the 6 gigabytes of file, you basically run very fast out of memory unless you buy a really, really powerful machine. Also, the system now was heavily used. So we uploaded, we found that 40 chapters are uploaded at once. Usually that means we have this 12 gigabytes in memory 40 times. So which is now basically burns down the cluster and also kills the hard disk drives. Also, what we detected that the pods are failing more often. The main reason is that we used for the analyzing, we used the spot instances. The main reason is the analyzing stage is computational intense and heavily, but on the other hand, not needed on a 24/7 basis. So we could rely on a much cheaper nodes than using the on-demand nodes. So to keep the costs also slower. And what we then did is we had to greatly focus on stability improvements, and which means we switched to a queue processing, and at another stage where we check the file size and split into chunks, because if we really have a chapter which is then more than 1 hour long, we can easily split it into smaller chunks of, let's say, 10 to 20 minutes, which is still long enough for the analyzer stage, but then fits again back into the nodes. And we also introduced the recovery strategy. So we're detecting the failing now of a processing stage and try to do it again or give proper error handling in that case. So how does the process now looks? So we again create the audiobook, then we create the chapter, we upload it, then we downloaded it, now in a queue, not in parallel, so that we do not overload the system. We split it again into it's also done in the queue. We have our PDF to text matching, and then of course we have to match again the text with the audio, analyze it, and retrieve the results. So, and after the third iteration, the whole system basically looks similar. We have now an additional part or service in the system, which is the chapter splitter, which now also checks the file size and keeps them manageable. Also, we changed now from a NAS to a bucket, also basically for storage reasons, because NAS are much more expensive than the bucket, and the bucket fits our needs. And with this, we are now at more.
Seems that we've lost our host.
I guess so, yeah, I'm afraid. I just pinged them. Let's see.
Sure, they will be back soon.
Yes. The WAV file behind it, but it's not clear whether, for instance, people has really uploaded all audio files, and it would be not customer if we miss a chapter on the book. So it would be nice to visualize somehow that really the whole book was covered via audio files, not only parts of it. And of course, we could do some additional architecture improvements, like using native frameworks or resources. So now the next steps with respect to the customers that wanted to go for a real life test parallel to an existing workflow to check the performance of the system again and how it performs now in a real world environment. Thank you very much. And also our customer together for the collaboration. And as side notes, here are the resources for the images if you're interested in. Otherwise, we are now open. Yes, I'll get the microphone.
Okay, please.
Yeah, thanks. Very interesting. I was wondering, you mentioned that you convert to characters. You have a table with the likelihood of characters. Have you considered how this might work if you try to extend this to English? Because I mean, English has a notoriously bad mapping between characters and the phonemes, I guess you'd get out of the audio stream.
Even the English model uses the character probability stream in between.
Yeah, it's basically a question of how well the architecture, the deep speech itself uses, just works on doing the speech to text, since it actually maps directly to the alphabet and not to like smaller chunks of characters or something like that. But I assume that actually our system would still perform better using an English model, just because the English model is trained on more data.
Thanks.
Thanks for the question. Any other questions from the room? Yes.
You mentioned that you had a chapter splitter added later.
Yes.
And as I understood, it was splitting the audio files. How do you know where to split the chapters in the audio files? Is there some queue in the audio file, or how does it work?
Basically, we are splitting it, I guess, something like every 20 minutes or so. And of course, it might be then the start and the end might be a little bit corrupted. On the other hand, what you can then do to improve it, to look for silence spots in there.
So these are not real chapters in a book, but like
it depends what you are uploading. So if you upload the whole book at once, at one audio file, then we split it basically in 20-minute chunks so that it fits to the computational resources, but it does not mean that these 20 minutes are really related to a chapter with respect to what the author mentioned or had in mind.
Okay. Yeah, and the timestamps at which these discrepancies are found afterwards are then obviously converted back to the timestamp in the original long file, so that you can go back to, so that the customer can go back to the original file that they uploaded and find the places in there.
Okay, thanks. Second question, is there a discrepancy in the result if you repeat the analysis?
No.
So it's basically pretty robust if you repeat. Okay.
There is no randomness.
One question from my side. Thank you for the talk. I was wondering about the error rate of deep speech. I would have expected, honestly, to be a bit better. Is my expectation that far off, or 7% error rate sounds relatively large to me compared to the corpus of text and speech that might be available? Are there other models out there that have, I don't know, substantially better or worse rate? Do you know of anything?
I think there are probably some just different architectures that can achieve a better result. When we started this project 1.5 years ago, this was state of the art. And so it might have evolved that there are some better speech-to-text engines so far. But I'm actually not sure the 7% error rate on what kind of test data this was run. It could have been also like, basically speech of people recording at home with not the best audio quality and so on. So,
thank you.
On the other hand, if you want to try it yourself, you can choose your favorite video platform and then enable the audio conversion, and then you will detect that it's basically on every second sentence it's wrong. There are some wrong words still.
Okay, any more questions? Yes, please.
Thank you for the talk. It was really interesting. Just a small question. How long have you been working now on the solution? So just to give an horizon.
Well, I started at TNG as an intern 1.5 years ago working on this project, and I spent 5 months full-time. And then since then, I've been working, because I'm still studying part-time as a student, basically one day a week, more or less. And Andreas has been contributing a couple hours a week.
Irregular. Regular.
Just supporting me, guiding me a bit towards or through technologies that I wasn't that familiar with before.
Okay, any more questions?
Could I also ask a question?
Yes, please go ahead.
More like in
so now that you have something that's, I mean, at least from the first numbers, it look quite good compared to the real world lectures. Is there any plans instead of just improving it to, like, is BOOKSTREAM using it in production, so to say, for the real audiobook validation, or is there any plans to make a product out of this, or to open source it, or to do anything else than just improving it technically, but to, like, what use cases do you see in the future? Like, or is it already used for like, are lectures already being replaced by this?
The next step would be to run it in parallel with the usual workflow. So next to it, to compare it. And then afterwards, we think that it will not replace the lectures, but the lectures will still be available, but more concentrate on the overall behavior of the audio, and now not so more on how true the text was read. So this is our current assumption.
So the last chance to ask your questions also in the Slack channel, but I think someone is writing. Okay, let's wait. Are there any more questions in the room? Any final thoughts? Yes.
Thank you for the talk. So I just have a non-technical question. Why did you decide to call it Hannibal?
This was not my idea.
Andreas?
You probably know this movie.
Yeah.
And there are similarities of the show name with respect to the work the machine does.
Thank you.
We have one more question from Slack. I'll bring you the microphone. Yeah, please.
Michael Schüßler asks, more of an ethical question. There is this whole discussion about AI taking away jobs. Hannibal helps to aid people doing their rather dull job, but what's your stance on that?
As mentioned, I think that the lectors will not gone, but they will concentrate more on the, let's say, non-technical review of the audiobooks. So more on the not focusing on whether all word suite, all chapters there, and all this more or less boring stuff, but more on the fun stuff, on how well was it spoken and such things which Hannibal can and will not judge.
Yeah, and the customer was concerned, especially with cases where entire paragraphs or pages were maybe missing from the audio, which is obviously a very severe mistake, which you don't want to happen, but which you can imagine if you're just listening to the audio, you can easily miss a mistake like that. If just like an entire chapter, for example, something is missing, you won't necessarily notice. And yeah, Hannibal can definitely add another layer of just security that such severe mistakes won't happen.
Thank you so much.
Okay, thanks for the answer. I see no more questions. Are there any? Do we have one last question in the room? If not, we will conclude our talk, and I will give a big thanks to Andreas and Tilman for presenting their really great machine learning project. And yeah, thanks for our audience. And yeah, following, we now have a coffee break for 30 minutes. So yeah, thanks. And
thank you.